Hello. So let us continue our discussion of the course. So we're going to be looking at convective momentum flux tensor quickly now. So you would have okay. So there are two tensors involved in the differential linear momentum balance that we discussed previously. Viscous stress tensor obviously that we know, and convective momentum flux tensor is also that. You see the convective terms in the x in the RHS of each momentum balance, we can group and write it as a convective momentum flux tensor. So this is how we represent it: rho VV, rho Vx, and these are all the components. Each column, if you see, would represent the convective terms in one of the momentum balances. Like this for x momentum balance, y momentum balance, z momentum balance. So we have grouped that together and written as convective momentum flux tensor. All right. So what is the dimensional interpretation of this? Rho into velocity into velocity. So velocity is nothing but volumetric flux. Rho into volumetric flux will be mass flux. Mass flux into velocity will be momentum flux. So it makes sense, right? And what does this represent? Rho v by vx. It is the convective flux of x momentum across y plane, across positive y plane, carried in the y direction, similar to what tau ix. Okay, tau ix is viscous stress acting along the positive x-axis, but it is acting on the positive y plane. Okay, let's move on. Okay, so what important thing we have to go through quickly? Material particle viewpoint of the linear momentum balance. So we all know that this is the substantial derivative, right? Rho into capital D by dt of the x velocity is written like this. We know that, and LHS of differential linear momentum balance for the x momentum can be simply written as this substantial derivative. And how do we obtain this? It's given in this slide. You can go through this. It's not, derivation is not that important. You can have a look at this, and obviously RHS will be the same, and this is the material particle form of the balance equation. And of course it stands for the Newton's second law, as in mass per unit volume times the acceleration of the particle is equal to the net force acting on the particle, right? It is in accordance with the Newton's second law of motion. Moving on. Okay, so another important concept is of degree of freedom analysis and the need for the closure problem. So to determine whether a system of equations can be solved or not, this degree of freedom analysis is important. So what is the DOF? It is written as number of unknown variables minus number of independent equations, where these equations could be partial differential, ordinary, or algebraic equations. Okay. Uh, so far we have all discussed one differential mass balance, three differential linear momentum balance x, y, z. Okay, and also let us consider the equation of state as shown below. For example, it could be ideal gas PV equal to PV equal to RT. So rho is equal to rho of P comma T. So totally, let's say we have five independent equations, and the number of independent variables, if you go back and have a look at the x linear momentum balance, you will notice that there is density. We have the three components of velocity, the pressure, and the viscous stress components, of which six of them will be independent, because the some of the diagonal elements of a viscous stress tensor is constant, right? So six of them will be independent. So total, if you add them all, you will get 11 independent variables. Clearly DOF is 11 minus 5 equal to 6, and since it's not 0, we cannot completely solve it, and we need to express the viscous stress tensor in terms of velocity or velocity gradients, and this is nothing but the closure problem. We need to close the system of equations. Moving on. Okay, so now this is important in our journey to close to close the system of equations: deformation and strain. There are two types of deformation. One is due to change in length, and the other is change in angle. Also there is a you can have change in both length and angle. And there are two measures of deformation: normal strain for change in length of a line element, and shear strain for the change in angle between two line elements. And all of this written at a point, let's say a point P in the object. So you can En represents normal strain, gamma nt represents the shear strain, and what is N and nt we'll see over here. So if this is the point we were considering, and let's take the small line segment PQ with length delta s, then along this is the vector n. All right, and what in this case, if you say change in angle, what is nnt? We have an angle created over here, PRQ. This is T and this is N. All right, and what is the definition of normal strain? Limit delta s tends to 0, delta star minus delta s by delta s. So basically it is nothing but the change in length of this PQ divided by delta s, as delta s tends to 0, is normal strain En at point P. And what will be the shear strain, gamma nt of P, it is pi by 2 minus the angle R star P star Q star. What is R star P star Q star? You see over here. R star is the new position of R, Q star is the new position of Q, and P star is new position of P. So initially angle we take it as 90, finally whatever it is angle R star P star Q star. So gamma int is defined like this, and note that if the normal strain is positive, that it implies increase in length, and if shear strain is positive, then it implies a decrease in the angle that we are looking at. Okay, now let's have a good notation. So let's just consider epsilon xx, epsilon yy, and epsilon zz. This is for convenience. Okay, epsilon xx is simply epsilon x only. That is the normal strain for line segment along x-axis. Similarly, for other axis, we have epsilon yy and epsilon zz. Okay. Now there's an important relation over here, that is gamma nt equal to gamma tn, that we have to remember. Basically, so we can say gamma x equal to gamma yx, and the sign convention would be in this case would be positive normal stress produces positive normal strain, negative normal stress would produce negative normal strain, and similarly for the shear stress and strain. Moving on. Okay, finally, we'll finish off this lecture with quickly going over this displacement field concept and displacement gradient. So the strain depends on the displacement of various points on the body, obviously. The displacement field is written on the basis of the deformed and the undeformed state. Okay, so the displacement gradient is given as difference in displacement of two adjacent particles. Okay, difference in displacement of two adjacent particles divided by the distance between them, same particles, either initial or final, and it is denoted like this: delta ux by delta x. Of course, in case of infinite small strain, doesn't matter if we are taking the initial or the final distance. Okay, between the particles. In the 2D case, ux will be equal to ux of x comma y, and uy will also depend on x and y of the particle we are considering, and therefore the displacement field will be given as shown. And for displacement gradient, okay, we'll have a 2 by 2 matrix as you can see over here, and in case of 3D we'll have a displacement gradient tensor with 9 components, as you can see: dou by dou x of ux, dou by dou f ux, dou by dou z of ux, and similarly for uy and uz. Thank you, and we will take it on from the next lecture.